Okay, so section 2, the rational numbers. Okay, so like we said, we're working our way to the real numbers. So we're working towards the real numbers, right? Right now, you finally stopped talking about the natural numbers. Right now, we're going to talk about the rational numbers, right? The natural numbers were these guys 1, 2, 3, etc. The integers are these guys 0, -1, 1, 2, -2, etc. Right? Integers. Okay, and the rational numbers. We're not going to, we're going to be kind of sloppy about this, but what are the rational numbers? What are the rational numbers? Too late. What are the rational numbers? Somebody tell me.
So it could be written as m over n, and m and n are both integers, but n wouldn't be 0.
Okay, so any quotient of the form, like m over n, where m and n are integers, and m is non-zero. Okay. Right, these are the rational numbers. Right, numbers which are expressed as quotients. Right, that's the reason for this cube. Right, it's a ratio. Right, that's the reason for the name rational. Right. Okay. This notation is, this is pretty, N, Z, and Q, and R is a standard notation. It's a so-called Bourbaki notation. Did I mention this already? Bourbaki notation? Okay. Yeah, I've seen, although Bourbaki was an imaginary person, I've actually seen a letter from him. People would try to invite him to conferences, and there was a letter in Indiana, like in the math department at Indiana, a polite refusal from Bourbaki saying, "I'm sorry, thank you for your invitation to the conference. I'm sorry I cannot make it. I'm an old man. Do not travel." Yeah. Okay. Okay, so there's this sort of progression, and each step basically remedies a flaw of the previous one, right? In the first one, you can add, right, but you can't sort of reverse the addition, right? If I add 2 to 1, there's nothing I can add back on to get back to 2, get back to 1, right? So I can say 1 plus 2, but there's nothing I can add. There's nothing I can add on to sort of reverse this addition, right? But once you have the integers, then it's possible, right? You can say, well, I'm going to add on this -2, and that gets me back home again, right? I started from 1, I added 2, I added -2, and I came back home to 1, right? So what the integers have that the natural numbers don't have are so-called additive inverses. So, right? No matter what you add, there's somebody that you can add on that cancels that effect. Okay. Right? What does Q have that Z does not have? Division, or the way we'd like to say it is probably multiplicative inverses, right? So you can multiply. If I multiply 1 by 2, you can multiply in the integers fine, right? Just like you can add in the natural numbers fine, right? You can multiply these guys and you stay in your system, right? If I have -1 times 1, I get -1. I don't leave Z. Right? I'm closed under, Z is closed, what they call closed under multiplication. But there's no multiplicative, there aren't multiplicative inverses for some elements, right? If I multiply by 2, there's nothing I can multiply to return to what I started off with, right? 1 times 2, well, I can't get back to 1 again, right? But if you have these things, then you've introduced. You're basically saying, well, let's throw in multiplicative inverses, right? So we add on, we adjoin multiplicative inverses. Okay. Okay. And then from Q to R, what do we adjoin to get to R from Q? What problem are we solving? What lack are we solving in Q? Because the lack is not completely obvious for Q. Right? What's wrong with Q? Why don't we just stay with Q? Right? The ancient Greeks stayed with it for quite some time and didn't really see any need to leave it. So what do we adjoin to Q to get to R? Okay, so there's a problem with Q. So there's a problem with Q. And the first hint of it that people got was first hint was this problem. Right? Suppose you have a right triangle. So we're back in the time of the ancient Greeks. Okay. For the Pythagoreans, the whole world was based on rational numbers. In fact, the whole universe was based on rational numbers. Right? They believed that when the planets moved around in the heavens, they did so in ratios. Right? If you have a string, like a cello string, and you pluck it, right? You cut it in half, you get something that's an octave higher. Right? If you cut it in thirds, what do you get? Does anyone know? Suppose you take a string and you cut it into thirds and you pluck it. What do you get? Any musicians? What you get is actually the note that is an octave and a fifth higher. An octave and a fifth higher. If you take it and you cut it into fourths, what do you get? Well, you cut it into half and half again, so you would get 2 octaves higher, right? Et cetera, et cetera. So the rational numbers, right? 1, 1/2, 1/3, blah blah blah, actually have for humans have this pleasing musical effect. And so they believe, for example, that there is this sort of song that was going on in the heavens constantly, right? Because everything was based on rational number. Okay. So the whole world is based on rational number. Okay. Then comes this question: if everything's rational number, what's this? What is the m over n? Did I call it m over n? Okay. What is the m over n for this number? For this number, right? For this number, what's the m over n for this? What m over n expresses this length, right? Okay. Okay. So you say, okay, well, what do you know about this? What do you know about this length? Let's call this thing x. What do you know about x? Do you know anything about x? What do you know about x? Tell me something you know about x.
2.
It's the square root of 2? Okay, so how do you know it's the square root of 2?
Yeah.
By the Pythagorean theorem. So by the Pythagorean theorem, x squared is equal to 2. Did we prove the Pythagorean theorem in this class? I don't remember. Did we prove the Pythagorean theorem? Okay, so maybe you've proved it already. So you can either say by Pythagorean theorem. There's actually another funny way to do it, and this is actually in Socrates, or it's in Plato's, one of Plato's dialogues, Meno. Socrates is trying to show that everybody has some innate knowledge. He's arguing with Meno, I think, and Socrates is saying, well, no, everybody actually has some mathematical knowledge in them, and he says he just calls over a passing slave, like there's a slave boy. He says, come over here. And he starts questioning, he starts, as in the way that Socrates does, he starts badgering the slave boy. And eventually he says, what is the square? If you have a triangle that looks like this, then what's the square of this? What's the square of x? Okay, and the argument that he pulls out of the boy is actually like this. He says, well, look, suppose you take 4 copies of that. Suppose you take 4 copies of that. Okay, so here's the same thing, right? Right. Then what's x squared? X squared is going to be the area of this square here, right? So what's the area? Now and then he keeps on badgering the guy and says, can you figure out what the area of this square is? He says, well, look, and suppose he makes the kid, add on an even larger square, and he says, well, what's the area of that square? What's the area of that square? Well, it's 4, right? 1, 2, 3, 4, right? Because each of these lengths is 1, right? Well, if the area of the big square is 4, then this thing is half of that, right? So the area of this thing is 2, right? And so x squared is 2, right? So this is how Socrates argues to Meno that everybody is capable of mathematical thinking. Okay. So So you have this thing, and you know that x squared is 2, right? And so it was a big question for them. What are the m and n that express this, right? What are the m and n that express this, right? And then eventually somebody, and I've forgotten his name. I've known him for many years, and it's just slipping my mind now. I'm sorry, I've forgotten his name. So somebody figured out that it's not even a rational number. There are no m and n that describe it. There are no m and n that describe it. We call it something like a logos or something like not describable, like beyond steps or something like that. Beyond steps. This is sort of like a precursor, of irrational, but not directly, but it's sort of the same idea. So the argument that person came up with goes like this. So it's not rational. It cannot be expressed as m over n. Okay. And I should say that there's another place in Plato where he says, nobody is worthy of the name of human. Like, nobody is human unless they understand this argument. Unless they understand why this is true. That's in another dialogue. Okay, so here's the argument. Suppose that x actually is rational, where m and n are in Z and n is not equal to Z. Suppose it can be expressed as a sort of ratio. Okay. In that case, then we know that either by Pythagorean theorem or by this argument, then we know that m squared over n squared equals 2. Right? By our picture or by the Pythagorean theorem over there. Right? X squared equals 2. Right? And so we make a simple deduction that, well then, m squared is equal to 2 n squared. Okay. Everyone all right? Okay. So in that case, notice then 2 divides the right-hand side, right? Certainly 2 divides cleanly this number over here, right, because it has a factor of 2, right? So 2 divides m squared, right? M squared is, these are the same number. M squared is 2m squared. The number on the right-hand side is even, so the number on the left is even, right? 2 divides this, so 2 divides that. Okay? Okay. So m squared is even, right? M squared is even. What am I going to say next? M squared is even. What do you know if m squared is even? What can you tell me if m squared is even? Don't blurt it out. Don't blurt it out. M is even. Yeah, so yeah, actually, thus, m is even. Right? And so, we should, to be proper, we should justify that, right? But it's I think it's clear, right? We want to show if m squared is even, then m is even. Okay. So here's one way you can do it. You can say, let's take the contrapositive statement. M odd implies m squared is odd. Okay, so this is something maybe, I don't know if you've seen it or not, but if you have a logical implication A implies B, so here's your statement, here's what's called the contrapositive. Not B implies not A. Okay. If you want to prove A equals B, it's equivalent, so these statements are actually equivalent. Okay. If you want to prove A implies B, you can just as well prove not B implies not A. Okay. So here's the statement, m squared is even implies m is even. Let's look at the contrapositive statement, m is odd implies m squared is odd. Okay. So let's prove that. You say, okay. Take a minute and prove that if m is odd, then m squared is odd. Take 1 minute and write down some reason why that is true. Okay, turn to somebody nearby and say, it's true because blah, 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 blah. Okay, who would like to say? Who would like to explain why if m is odd, then m squared has to be odd? Yeah?
If 2 doesn't divide into m, multiplying m by itself isn't going to change that.
If
If
2
just like
doesn't divide m, then
2 won't divide into m times m because it won't divide into either of the m's.
then 2 doesn't divide m times m.
Or I wrote it as like m can be represented as 2k plus 1.
M being odd is 2k plus 1, so k is some integer.
And then I squared 2k plus 1.
Okay, that's that. The first one makes me a little worried that we're just rephrasing.
Yeah.
that we need to use another statement. This one is more straightforward. Right? So to square it, right? So you get 4k squared plus 4k plus 1. And you see that this thing is even plus 1, right? Which is odd. Okay. So we prove the contrapositive, and so that gives us this thing. If m squared is even, then m is even. So we justify it. Okay, so m is even, right? So m equals 2k for some k in z, right? Okay, now going back here, what we get, going back to this box statement, what we get is, does anyone see how we're gonna finish things up? Let me first add in something that I forgot to throw in here. We can assume, without loss of generality, can assume m and n have no common factors. Right, that you put it in lowest terms. Right, if they're common fact, if you had like 2 times 3 and 2 times 4, just make it, instead of 6 and 8, just take 3 and 4. So take out the common factors. Yeah, Emily.
What is WLG?
Without loss of generality, so without weakening our argument, it doesn't cost us anything to divide at this point. Okay, so then, let's see what happens. M is 2k, so we get 2k squared equals 2n squared. In other words, 4k squared equals 2n squared. So 2k squared equals n squared. Right? Okay. Take another minute. What do you see happens? Mia.
N is even.
N is even. Great. Then n is even also. Right? Because by the same argument, right? N squared is even, so n is even. Same argument. Okay. So what do we get? We get that if thus if x equals m over n, or x squared equals 2, we see m and n have no common factors. And m and n, right? So thus, m and n have no common factors, and m and n are both even. Okay. Does that bother you? It's a contradiction, right? This is impossible, right? We're saying that we assume that they have no common factors, but we see that they're both even. Okay. So, what we're saying is that if this guy is rational, then we end up with this craziness. Okay. If this guy is rational, then you end up with this craziness. Okay. And so x could not have been rational. And usually you say contradiction. Contradiction. And you put some symbol. Or you put like this symbol. These are both symbols for contradiction. Like got two things going against each other. Or this symbol. I don't know. Both of these are common symbols for contradiction. So x could not have been rational. And so this is the argument that the person gave 2,500 years ago that blew apart the Pythagorean system of reality. And apparently caused him to get murdered. So they killed him. The story is that they were on a boat. I wish I remembered his name. They were on a boat, and he suddenly comes up. There is no rational number that expresses this length, and he explains it to them, and they're so upset that he's destroyed their reality that they throw him over the edge. That's the story. It's probably not true. Okay, that's it for today. That's it for today. Yeah, so I should say that at the beginning you have to justify everything. It's kind of a pain and it's irritating, but later on we'll ease up on that. But for now, please just justify everything.